picking up where we left off in the previous lesson, where we can rewrite difficult trig functions using identities so that they're set up for easier evaluation. We want to look at the case, still talking about sine and cosine, but we want to look at the case this time where m and n are even. So in our previous lesson, we weren't worried about which power was even. We were looking for an odd power, and the other one went along for the ride. In this case, m and n are both even, and you need to remember that 0 is even. 0 is an even number. So in this case, we're going to use power reducing identities. So remember that the sine squared of x equals 1 minus cos of 2x, so we've doubled the angle, but we've reduced the power over 2. And the cos squared of x is almost the same thing, except there's a plus sign. All right, so let's do an example. I think by now the process is pretty clear. Let's do a relatively simple looking problem. We're going to take the cosine to the 4th power of x dx, and we want to evaluate this integral. So I could go right to substitution, right? U cos x equals u, but du would be sine x dx, and we don't have that here. So we're going to use the power reducing identity for cos squared of x. So that means I want cos squared of x equal to, I'm going to write it this way, just because I think it'll be easier for me to work with. But I don't want cos squared of x, I want cos to the 4th, which means if I square both sides, then I end up with cos to the 4th of x equals, well, 1/2 squared is 1/4. I can pull that out, and then I can distribute this. 1 plus 2 cos 2x plus cos squared of 2x. So now I'm going to make the substitution. 1/4 is a constant, so I'll pull it out front. I think I'll keep everything together for now. 1 plus 2 cos 2x plus cos squared of 2x dx. Now if I distribute dx into each one and separate into separate integrals, if I distribute dx into each term and separate into different integrals, I get the antiderivative of dx plus 2 times the antiderivative of cos 2x dx plus the antiderivative of cos squared 2x. Now I have 3 separate integrals to calculate. Each in turn will be multiplied by 1/4. But before I get in there and get my hands dirty, let's have a look at each of these integrals. This first one, easy peasy, right? We know that this is a direct integration or a direct antiderivative calculation where the antiderivative equals x. This middle one, though, not counting or including the constant, just finding the cosine of 2x, this is going to involve a substitution where I let u equal 2x. So du would be 2 times dx, or 2 dx, and now divide through 1/2 du equals dx. So I would substitute 1/2 du for the dx, and then I could put the 2x or u in for 2x and then integrate from there. But this last one, this is the tricky one. What do I have here? Well, I just have a repeated calculation using the power reducing identity. This one is going to use cos squared of 2x, where 2x is just my angle, equals 1/2 times 1 plus the cos of, well, 2x being my angle. Don't get confused in the x's. This is an x that's just a placeholder for the identity. This is an x that's a variable in my problem I'm solving. But if I wanted the cos of 2 times the angle, well, 2 times 2x is just 4x. So in this case, I'm going to substitute this identity for cos of 2x, and then I think I'll be able to get there. Okay, so let's go ahead and do that. I have 1/4 out front, x, okay, we're happy with that one, plus, well, 2 times, I'm still looking for the integral of the cosine of u du, but du has to be divided by 2. So that 2 is going to disappear on me, which is nice. 2 divided by 2 is just going to be a 1. Plus the antiderivative of 1/2. Well, that can go out front. No sense beating about the bush. Get that out of the way right away. 1 plus cos of 4x dx. And we can see exactly where we're headed at this stage of the game, because now I'm just going to separate these into 2 separate integrations. So continuing on, 1/4 x plus the antiderivative of cos u is sine u, but I'm going to go ahead and substitute my 2x back in, plus 1/2 times, and I'm going to separate these, the antiderivative of 1 dx plus the antiderivative of cos 4x dx. Okay, where am I now? 1/4 x plus sine of 2x plus 1/2 times antiderivative of 1 is x plus 1/4 times the sine of 4x. Now you may be wondering how I got there. Truth is, all I did was a substitution, a u substitution just like this one, where instead of 2x I substituted for 4x, and it would probably behoove you to double check my work, but I'm pretty confident in it. So let's go ahead and put this back together. 1/4 times x plus 1/4 times sine of 2x plus, well, what do I have? I have 1/2 times x times 1/4 is going to be 1/8 x plus 1/2 times 1/4 is 1/8 times 1/4 is 1/32, or 1/32 sine of 4x. Let me take a second to double check against my notes. Oh, and it all looks good except for combining these two terms. So 1/4 plus 1/8 is 3/8 x plus 1/4 sine 2x plus 1/32 sine 4x plus c. Don't forget that plus c, you always have to have it. Well, I think time allows for another example. I think I won't go into great detail about substitutions and algebra, but I'll take you through the steps. So we want to find the sine squared of x times the cos to the 4th of x dx. And in this case, we're looking at 2 is even and 4 is even, so we want to use the power reducing form of identity. So if I rewrite this, I can have, well, the sine squared of x is just 1/2 times 1 minus cos of 2x times, again, in this case I've got the cos to the 4th, so it's the same substitution I did before, 1/2 times 1 plus cos of 2x. And all of that is dx. Oh, I'm sorry, this is squared at this stage. So I can pull out the 1/2. Thank goodness that's out of my way. So this 1/2 has to be squared, which is 1/4 times 1/2 is 1/8 times the antiderivative 1 minus cos 2x times 1 plus cos 2x. This is starting to look pretty familiar from algebra. So that gives me 1/8 times the antiderivative. Oh, I forgot my square up here. So I guess I lied to you. I think I probably will go through the process. I'm going to use a direct substitution. So instead of the cos of 2x, right? So I'm going to do a substitution over here that lets a equal the cos of 2x. Now, this is not for integration. This is for algebra. If a equals the cos of 2x, then what I'm looking at is distributing 1 minus a times 1 plus a squared. See how all I've done is rewritten this in a way that's much more manageable, much less likely to make a bunch of mistakes. First, I want to distribute this. So I have 1 minus a times 1 plus 2a plus a squared. If I distribute this 1 into each part of this and then negative a into 1 into each term of the second number, negative a into each term of the second number, I end up with, bam, I did that off page so you didn't have to watch me go through it. All I did was do those distributions, and then this was adding like terms. So this is what I get when I distribute these binomials. But a in this case has to be my cos of 2x's. So let's just put it together. I'm looking at 1, which is just 1. Let's do this. Minus cos of 2a, or excuse me, cos of 2x, minus cos squared 2x, minus cos cubed of 2x, all dx. Now let's separate them into separate integrals. I still have my 1/8 out front. I'm going to take the antiderivative of 1 dx minus the antiderivative of cos 2x dx minus the antiderivative of cos squared of 2x dx minus the antiderivative of cos cubed 2x dx. And let's look at what we're dealing with. So this one, easy peasy, x. This one is going to use a u substitution. U equals 2x. So du equals 2 dx. For the third antiderivative, we're looking at cos 2x is squared, which is even. Sine of 2x is to the 0 power, which is even. So we're going to use the power reducing identity. And we get 1/2 times the antiderivative of 1 plus cos 4x dx. And finally, the last antiderivative is of the form m or n is odd. So I'm going to rewrite my function and substitute in my cos squared of 2x using the Pythagorean identity, cos squared 2x plus sine squared 2x equals 1. So while I kept saying I was going to do these things, the truth is you're going to do these things, and I'll give you the final answer so you can check your work. So the final answer is x over 16 minus the sine of 4x over 64 plus sine squared, or excuse me, sine cubed of 2x over 48 plus c. So you should try your hand at each of these methods. This should be your final answer, and that'll do it. So that finishes up integrations on products of powers of sine and cosine functions. Next time we'll move on to other trig functions using even and odd powers to integrate.